For many years, one of the largest contributors to the OS pool has been Syracuse University, and we sometimes wonder where they get all their machines. And it turns out they're always looking for more machines. And Peter's going to tell us how they find even more machines. So our next speaker from Syracuse is Peter Pizzimenti.
Thank you very much. Okay. Hello, everyone. My name is Peter Pizzimenti from Syracuse University. A little bit about me is that I like talking and I like coffee. So I'm in an excellent place right now. I got my coffee and I'm doing my talking. So what do I want to talk about today? I want to talk about elastically bursting in the cloud for our on-prem HTCondor cluster that we call OrangeGrid. There is some restraints that I put on myself and on the team for how we wanted to do this and how we'd roll it out to our users. And I kind of sum it up in this in that gray box there. Now for the user, it is the same workflow that they experience today on-prem. It's the same submit file syntax that they use today. And most importantly, when it comes to making this transparent to them, is the same storage model. So while part of this presentation will be talking about or kind of focusing on that storage model, what I really want to be able to or have everyone kind of take away today is not necessarily the solution as a whole, because it may or may not be useful to you. But what I'm hoping is throughout the talking about the pieces of technology that we're using, that you'll find some diamonds in the rough. It's like, well, maybe not all this is what I need, but that little piece would probably be very helpful. So we can talk about it as a solution or a list of things that Pete found that seems pretty cool that I'd like to show to all his friends. So what are we going to talk about today? We're going to talk about the why. This focused tool set. This tool set with a focus, I should say more, and why we built it, and how I'll give you an architectural overview. We'll look at a graph of or a mermaid graph of this whole thing. And we're going to talk about the deployment of these elastic nodes in the cloud. And we're going to talk about the compute layer and the storage layer. Next, I'm going to give you some performance numbers, what this looks like in our beta testing when we're actually running in this particular workflow. And I'm going to show you an MCP server that we built to help with capacity planning and purchasing. And we're going to talk about how this is a batteries included solution that I am not looking to any particular cloud for my resources. I'm looking to any cloud, be it public or private. It could be Azure, GCP, or Joe's Clam Shack and Discount Virtual Machines. If they can provide me a Linux endpoint and an IP address, that's enough. That's enough for me to consume their resources in a way that users on-prem with certain requirements can consume. And then we're going to talk about the future, what's next, and some of my key takeaways. So a little bit of disclaimer, a little bit of some more understanding. What this is a framework tooling to add capacity to our on-prem HTCondor pool. Do it in a way that is transparent to the researcher. It's important that I do not bifurcate my cluster. If I am going to add these resources to my cluster, I don't want to have to retrain or tell my researchers, hey, between Tuesday and Thursday, I'm going to be adding 1,000 cores. Please add such and such line to your submit file or use this different submitter. I don't want to retrain. I just want them to consume when they have the ability to do so. So how do we do this? Big part of that is making sure that their storage layer that they're currently using is available to the cloud. So yes, there be dragons. I am using NFS over WAN. It is usable. in a lot of cases, not in all, and I will show that and where it works and where it doesn't. And then, as a whole, this being built around our environment and our constraints. What it isn't, this isn't a replacement for Annex or Glidden. It's another menu option. I'm not saying throw any of that away. I'm saying keep that and this. It's not an either or, it's an and. It's not a replacement for HTCondor file transfer. It is, again, yet another option. It's not a replacement for CVMFS or Pelican. It's yet another option. And more importantly, it is not a universal solution. I have a particular itch. This scratches it. And it may be helpful for you also. So why did we build it? Some universals here. Research demand can be bursty. At the end of the semester, graduate students need to graduate. They want to get their work done and they want to get out. And I want to be able to provide them the resources to get their work done in a timely fashion. Buying hardware for peak is expensive. You can only have one peak. And then when your next peak, well, your last peak isn't your peak anymore. So when buying for that peak, that means you're always going to have idle. Always want just enough. And when I have more work than I have cluster, I want to use this as a pressure release valve. So I'm going to add just a little bit here, a little bit there, like bring that queue down. I want to make sure that researchers can continue to use their home directory, their POSIX home directory, in the same way that they've always have, because I don't want to retrain. I can build something a little bit more complicated on the back end on my time, but I got to train them on their time. And then we are all creatures of habit. Back to that training, I can have that training, and I should, and I do. But I can't train everybody all at the same time with all the same information. I can get some, and that some may use it, that some may not, that some may forget, and therefore I have less that consume this particular thing. So requirements, user changes nothing. They work the way they work today on-prem is the way they'd work in the cloud. I don't want them to know. I want to be able to add capacity, and their work goes there if it needs to, and if it doesn't, it won't. The data follows the workload. I don't want them to have to pre-stage their data. I want to do that on their behalf, or have their first job run pay for that slow read over a WAN. Therefore, their second job run runs quickly because it is cached at that remote site. I want to be able to use compute from anywhere. Much like I said before, I don't want to be tied to any one cloud or any one provider. I don't want to use necessarily their technology. I just want to consume their base level fundamental components, CPU, GPU storage. And what I need from them is very little. I need Linux, I need Docker, I need the internet. If you can give me those, that is enough for me to consume your resource. And like I said, I do not want to bifurcate my cluster. I do not want to have certain rules for this part and another set of rules for that part. I want to mush it all together, and everyone can use it when it's available. So, architectural overview. There's a lot in this slide. I'll come back to this for questions if everyone has them, but this is roughly kind of what this looks like. I have my public cloud part, which is mostly my worker nodes that are just in time. They're relatively boring. Not a whole lot going on here, much like any other worker node. The CPU, we got some GPUs, we got storage, we got just enough storage, not enough storage, just enough to do the work. And then we have this server, a NFSD cache proxy. This is the tool that allows me to re-export their home directories into the WAN. And on this is another cache. And this cache is very large. So you as a user, you make your first call on your file goes into this cache, it's a central cache, and then that cache can provide that data as read to all my other worker nodes. So why do this? Why not have caches all over the place? I don't want to pay for 100% of the storage on every worker node. I want to pay for just enough storage for them to get work done, and then use this central cache to populate my reads for everybody else. And on the bottom is the on-prem pieces like my provisioner, my lighthouse, which I'll talk about, my relays and how we get back, my central manager, my LDAP, and my NetApp backend storage. Okay, so the cloud worker deployment process, again, with the idea of using very little of a vendor-specific technology. I want to use the base layer tools. So how am I getting these nodes spun up? Well, I am bound by a minimal of using the tooling that is provided, or at least the APIs provided by the cloud provider to first start up. But at that point, I pick up. I use simple things like Cloud Init. I give it just enough to bootstrap. I give it all the information that it needs to get all the other pieces from the internet. So what happens? Turn it on, Cloud Init. Cloud Init gives it the bootstrap information. It says, go to this GitHub repo. There's a Docker Compose file waiting for you. Grab that. That has all the software you need. Grab that and then grab your images. Then I need you to connect to the network. How are you going to do that? Here is a TLS cert. So you can talk to my provisioner API, and you need this cert to authenticate using MTLS. So my web server is open to the internet, but you got to have this cert to talk to my API. This cert, this MTLS, hides all my sins. I haven't written a whole lot of APIs, so I can't trust in myself that I'm doing the absolute best job. So instead of putting that API on the open web, what I'm doing is sticking MTLS in front of it and letting the web server do a very broad deny of everybody unless you have your cert. Talk to this provisioner. This provisioner says, hey, you're a new virtual machine. I need a little bit of information from you. I need your public IP address if you got one. You don't necessarily need to have one, but if you got it, I need it. And next is, here's another cert. I need you to connect to my overlay network. I need you to connect to this network that logically puts you on the same plane of all my other machines on-prem. This overlay network creates a new flat logical network that doesn't care about firewalls. It doesn't care about NAT. It doesn't care about the rules that you've set up in between for the most part. And allows this machine to sit on the same network logically in a mesh with all the other machines, both in the cloud and on-prem. And it does that through an application called Nebula. So it is connected. It is provisioned. Provisioner has given it a address on my flat overlay network. It is then handed a bundle of information, like this is how you configure yourself to be a part of OrangeGrid. It's given some creds, some configuration, an IP address, and then it allows it to start talking to LDAP, and then it registers itself into my pool. And at that point, it starts accepting jobs. So the compute layer. So we talked about how to get that compute up. This is what happens when the compute comes up. This is beautifully boring. This is like all the other compute that we've set up. I didn't want to make this particularly hard or difficult. I wanted feature parity with worker nodes that I have on campus. So a researcher here can consume a resource there. So what does it look like? It is an execute node running the HTCondor LTS Docker image. What did I add to it? I added it a Nebula overlay network so it could look and feel like it's sitting on-prem, nice flat subnet. How is it connected to storage? NFS v42. How does that home directory get connected? Through AutoFS when a researcher's jobs lands on that node. Where does it get that information? It gets that information from LDAP. How do I manage the life cycle? Well, I watch some of the health processes of that machine. So the life cycle, the workflow, it only really has two states: on and destroyed. Once a machine is up, I don't plan for it to be up for very long. These things are ephemeral and very expensive. It is there just enough to relieve pressure to my cluster. And when I don't need it anymore, I throw it away. So next is the storage layer. So this is one of the ways that we're taking that NFS traffic and pushing it into the cloud. I'm using a tool called KNFS cache utils. So this is a kernel NFS proxy exporter with FS cache built into it. 5 minutes. This allows for that when a job comes in, that first read, they're going to pay the tax of going over the WAN. And then once they hit this cache, those files sit there for allowing all the other workers to benefit from that person that went first. Again, connected to a Nebula network, and then back to my on-campus storage. So the design goals, just in time staging, that the job ran and needs these specific files, regardless of what is in the directory. If the job or the binary doesn't ask for it, I don't move it because it never was read. The campus storage configuration doesn't change. The workflow doesn't change. One of the interesting things in here is I can do a little bit of smart pre-caching, a little smart pre-warming. Because I can see both ends, when this exporter comes up, you see, hey, this person runs Conda. This person has run Conda the last 7 days. So what I can do is this exporter, I have a little shim, looks at the Conda manifest file, like, oh, look at this environment. Chances are, if they're running here, they're going to need this. There's a lazy lookup process that runs slowly in the background and starts reading those files in on the behalf of the researcher. I'm not asking them to do anything. I'm making a guess. I need to be more right than wrong, and that's success. If for whatever reason that I missed a hit, then that first read, they're going to pay the tax, but they're only going to pay it once. So performance metrics, what does this look like when you actually run it? When you run the NFS over a WAN. Okay, so I have a few jobs here, and I try to take what an average HTCondor job looked like, if you could even do such a thing. But I said some common examples. So I used Blender. I felt like this was a good tool, a good way for people like see something big that can be broken up into small pieces and run individually. So I have a scene that I want to render. It has 240 frames. I use Blender as an Aptainer container as my binary. Read that stuff in, it comes up. So on-prem, it took 6 minutes and 48 seconds. In the cloud, for that entire process, the wall clock took 6.64 seconds, 6.64 minutes, apologies. To do the entire rendering, it took 13 and a half minutes. To do that same job in the cloud, it took about 19 minutes. So then my next 4, a little bit different. These are compute heavy ones. What I didn't want to do is, hey, look, I started this Python job and I had to wait for 3 minutes. I had 3 minutes sleep. Look how fast it is. It didn't do anything. But I offset that, but by the very bottom, the 2,000 file metadata workflow. This is terrible. This is half a second on the cluster on-prem, and this is about 9.5 minutes on the WAN. So this informed me. It's like, this isn't a universal solution. This isn't everything for everyone. It is some for most. And since I have the information of my cluster and my users and how they do things, I can make a choice of this is a good job for it to go into the cloud when I have contention, and maybe this job isn't. So another piece I want to talk about is capacity planning. So we wrote an MCP server that connects to cloud pricing and to our storage and to our historical job information. So I can ask it questions. I can ask it questions. Hey, I got $500. What is the most amount of capacity I can rent for the next 24 hours? And what it does, there's a couple of rules in the back. So I got stay on the East Coast, look at these 3 cloud providers, and tell me what you can do for $500. Well, looking at right now market prices like buying lobster, the GCP, I can get you 3,800 cores for about $500. Looking at today's market and spot. cool, that's interesting. Maybe I can make a choice of that. So back to the contention. How long should we rent cloud GPUs to clear today's HTCondor GPU queue? Well, you have about 550 jobs waiting in the queue. Looked at who's running and what they're doing. It's like, they need one GPU, 16 cores, 16 gigs of memory, and based on their previous runs, it usually takes about 22 hours. But when I add a little bit of time, maybe 24. If you want to be sure, add about 30. Doing that, it costs you about 4K to get, 550 GPUs across these two clouds. So just another way exposing this information, make choices if and when I want to turn this pressure release valve. So in closing, I want to talk about, so today it's in Azure because that was a path of least resistance, have some familiar in there. But tomorrow I want to go to AWS, GCP, NeoClouds, other universities, private and other private infrastructure. I don't care where it ends up. I will bring the batteries. I will bring all the tools that it needs for it to work. You just need to give me a Linux endpoint, and that should be enough. So what's next? As of right now, a little bit of a beta. Success, I want to open up to everybody, everyone that can use it. I want to automate my cloud consumption using the MCP tool that I've shown already. I want to use historical job information. I want to use statistics. I want to use what their storage profile looks like, how many IOPS, how much storage they use to make choices on what jobs go where. I want to burst the GPUs. I focus on CPUs today as to lower my variables. GPUs shouldn't be a big reach. And then lastly, I want to be able to reach more clouds, go wherever the capacity may be. Questions?
So you say I have $300.
Yep.
In your world, where do you assume the $300 are coming from?
Okay.
Do you have a printer in the basement?
Oh yeah. Oh yeah.
So let's start with, I believe, the hard part of it.
Okay. So you want to
where's the money? Where's the money coming from?
Okay, you want to talk about the accounting? Okay, so it's Syracuse.
Everything else caching.
Okay.
I have other question about it, but I don't know. It all starts with the $500.
Got it. So where does this come from? So at Syracuse University, all research computing is funded by the university.
Yeah.
So
so it's your money.
It is my money.
So how are you going to decide to put aside $500 for whatever, the number, rather than using it
to buy
hardware? I don't know, for pizza. I don't know what is the, I'm trying to understand, at the end of the day, you have a budget.
I do.
And you have to decide how much of it you buy on-prem and how much do you keep aside for that.
Yeah.
So I wonder how do you think about going about it?
So the idea is, again, this being a pressure release valve, and then using historical information, I've seen that I have bursted and it's cost me X amount of dollars last year. And it's cost me Y amount of dollars the year before. And that will start informing, like, maybe I do not have enough on-prem to meet the need on-prem. So that I can start making choices after maybe that first year or the first couple, of saying that, okay, if I'm using my pressure release valve all the time, then I have a problem with pressure, and I should
So you are saying, because I haven't seen here the criteria of whether what you're doing is good or not, in terms of the impact on the researchers in, okay, there's a queue of GPUs. Yeah. How much difference does it make to research in Syracuse that you drain it or not over the year rather than keeping the $500 when you need it, or going to a vendor and giving them the $500 to buy hardware?
I think what we'll be doing is we'll be asking ourselves question, did it take less time to wait? And if it did, was using this cheaper than buying to reach a certain number that we're comfortable with? And when we would do it, we look at historical information on when we've seen a lot of contention, and we can also cross-reference that through tickets. People have said, it's like, hey, like we get enough of like, this is a season where I go to speak, and I need something for right now. So how do I get there? If we're looking for the cold-hearted answer of when it's happening via spreadsheet, I don't have that answer for you. So right now is like, it's a little bit of a gut. Like, I have dollars to spend, and I don't spend it on myself. It's not, I don't buy it for me, I buy it for them.
You know, I'm thinking here in terms of campus, other campuses that are coming in and saying, okay, is that something I should follow or not? And you are sold to it, you like it, it gives you also, I would argue, some interesting stuff to do. But if I walk in, I think we have to communicate how a new campus showing up saying, should I follow it or not? And how am I going to manage it?
Got it. I think you could look at that, with your surplus dollars, which no one really has, but you could say, like, maybe I have 500. That isn't enough to buy anything of consequence at the data center. But does that $500 at 4,000 cores, does that make, for me, when I look at mine, right, does 4,000 cores make a difference? Like, and that depends on scale. If I have 400,000 cores, maybe another 400 or 4,000 doesn't make much difference. But if I have 10,000 and I have $500, then maybe it does. Maybe it does long enough.
Maybe.
Maybe. Oh yeah, this is all maybe. This is some for most, not everything for everyone.
And how do you factor in all the pieces that you have to put in around it? You have to run a cache, you have to run there are a lot of moving parts that may or may not cost you money to deal with them beyond the $500 that go for the rental.
Yeah, absolutely. So like the caching piece, the proxy server, that it doesn't come at any cost. That does have a cost.
No, but there's additional complexity.
That is true.
Which costs money.
It costs money too. Yes, it does cost money. It also costs time. I deal in two currencies, time and money. Absolutely.
Time is, yeah, okay.
So, can I break in here? So, you mentioned in talking to Marone here that you were going to use historical precedent to make decisions, but that brought to my mind that I know the difficulties Fermilab has had in just the past couple of months to buy equipment. And so it does seem to me that the AI boom and, quadrupling of memory prices, all of that has thrown all of our historical knowledge into the trash. And I was wondering what you think about that and what you're going to do about it.
So I would say that we've as a university, we have an agreement with Claude, and the very initially providing Claude AI to all faculty, staff, and students. What we found specifically on the cluster and the cluster pressure is people stopped asking to use the cluster to make another chatbot. So that helped quite a bit. They were able to consume that in a way that they were trying to consume the cluster, because they were looking at the cluster as a destination. This was their final step. I need some GPUs. What you need is inferencing. And what you're looking at the cluster, you're looking at the GPU as your final destination. It isn't your final destination. If I told you you could do inferencing on a bushel of apples, like, would you care? No, not so much. Like it is how do I get to that end goal? So we were able to scratch that particular itch of, making the chatbots with something like Claude. Again, not for everyone. It happens to work for us, which then at that point allowed other workloads that wasn't recreating the chatbot to go back in the cluster, not have to wait in that queue. So again, do we still have that work? Will we still have that work? Absolutely. Yeah. And it'll be a learning process. We'll have to make choices on when to turn that valve, when to release the pressure, depending on, requests or tickets or timelines. But I wanted to make sure I had that option. I didn't want my only option is, I have to spend $500,000 on a GPU server, because I'm seeing a lot of contention. I wanted something in between nothing and $500,000 or $2 million. This is my in between.
Just one quick Zoom question. How reliable do you find mounting home directories over the internet? How easy is it to identify and fix?
Say again?
How reliable do you find mounting home directories over the internet? How easy is it to identify and fix?
So just general issues on how.
The Zoom question.
Got it. So what happens is this starts up, it queries LDAP. The LDAP has the home directory information, and then we'll attempt to mount the home directory. We have a lot of users in our LDAP. So what we've put in is to not do everything for everyone, because we'll never need everyone to use it. If I have an everyone for everything problem, this isn't the solution. So what we do is we have an allow list. I can put net IDs in a list to only mount certain things, as to limit my scope of how many I'm trying to serve at any one time. What would I use to troubleshoot it? All the same tools I use currently, because it's a lot of the same. It's got a different coat of paint, but a mounting of an NFS home directory, and all those issues, using AutoFS or reading the home directory, all those pieces, they're all the same. They're in a slightly different place, but my troubleshooting hasn't changed that whole lot.
Okay, let's thank our speaker again. Thank you, Peter.